Let's begin with a simple idea. Sometimes the chemistry isn't the problem, the process is. In custom polymer synthesis, we often focus so heavily on performance that we forget the hidden cost behind the scenes, the solvents, the catalysts, the energy, and the waste. Green chemistry offers a way forward, not as a constraint, but as a framework that transforms how we design, synthesize, and scale polymers. In this session, we'll explore how sustainable chemistry is reshaping polymer innovation from the ground up. Green chemistry is frequently reduced to a buzzword, something about being eco-friendly or reducing waste. But in reality, it's much deeper. Green chemistry is a design framework built on 12 guiding principles that help us engineer safer molecules and safer manufacturing routes from the very beginning. And when we apply these principles to custom polymer synthesis, we don't just improve the final material, we influence the entire polymer life cycle. From the moment we choose our monomers to reaction conditions, purification methods, and even how that polymer returns to the environment or re-enters the value chain. Green chemistry is not just about improving a polymer, it's about improving the path we take to make it. Traditional polymer synthesis works, but at a cost. Many processes are solvent-heavy, relying on large volumes of hazardous organic solvents. Metal catalysts, while effective, can be difficult to fully remove and pose contamination risks. High-temperature reactions consume enormous energy and limit the types of materials we can produce. And of course, waste streams, often large, difficult to treat, and expensive to dispose of, add another layer of complexity. As projects scale from the bench to pilot to commercial volumes, these issues grow exponentially. Green chemistry doesn't change the functionality you want, it simply offers a cleaner, safer, more efficient path to achieve it. Every polymer starts with a monomer, and that makes monomer design one of the most powerful levers in green chemistry. The goal of Principle 1 is simple: design molecules that are inherently safer. Bio-based monomers are excellent examples. Lactic acid gives us PLA, biodegradable plastics with great processability. Itaconic acid opens the door to renewable acrylates that replace petrochemical routes. And furan-based monomers derived from biomass can substitute for aromatic building blocks from petroleum. Choosing these monomers doesn't just reduce hazards, it builds sustainability directly into the polymer backbone itself, right from the start. Solvents are often the biggest environmental challenge in polymer synthesis. They influence reaction rates, heat transfer, purification, and waste generation. Switching solvents can feel like changing the entire personality of a reaction, but when chosen well, it can be transformative. Supercritical CO2, for example, is non-toxic, non-flammable, and can eliminate the need for organic solvents in certain polymerizations. Ionic liquids offer high tunability and can support controlled polymerizations with easy recyclability. And waterborne systems, now widely adopted, provide cleaner, safer reaction environments with better heat management. Beyond the environmental benefits, safer solvents often lead to simpler purification, better reaction control, and ultimately, more consistent product quality. This principle is one of the most transformative for polymer chemistry. Traditional polymerization often relies on stoichiometric initiators or metal-based catalysts that generate large amounts of waste and require high energy. Catalysis flips this script. With catalysts, reactions become more selective, require less energy, and produce less waste. Organocatalysts allow metal-free ring-opening polymerization, which is ideal for medical or electronic applications where purity is essential. Enzyme-catalyzed polymerizations run at mild temperatures and neutral pH, delivering sustainability and performance together. In fact, biocatalytic polyester synthesis has demonstrated up to a 60% reduction in energy consumption, a real-world proof of the power of green catalysis. Energy is one of the hidden costs in polymer production. Many polymerizations run at extremely high temperatures, consuming large amounts of energy and limiting material choices. Green chemistry asks a simple question: can we achieve the same chemistry with less energy? And the answer is often yes. Microwave-assisted polymerization dramatically speeds up reactions while using far less energy. Photopolymerization, initiated by UV or visible light, is now central to 3D printing and advanced coatings. Room temperature redox initiation eliminates the need for heating altogether. Lower activation energy means lower cost, lower emissions, and more flexibility in process design. For decades, polymers were designed to last forever. But now we're designing them with intentional degradation pathways and circular life cycles. Chemically recyclable polymers, like polydiketoenamines, can depolymerize back into monomers. Biodegradable systems, such as PLA, PCl, and PBS, return to the environment naturally. And depolymerizable monomers in controlled radical polymerizations allow polymers to be reversed back to their building blocks. This shift from permanence to planned circularity ensures that polymers don't end up in landfills or incinerators, but instead become part of a sustainable materials loop. Let's look at a real example of how powerful these principles can be when used together. A specialty polyurethane manufacturer set a goal: reduce hazardous waste by 40%. Here's how they achieved far more than that. They switched to bio-based polyols, removing dependence on petro-derived feedstocks. They replaced tin-based catalysts with organocatalysts, eliminating metal contamination. They redesigned the process to be solvent-free. And they introduced depolymerization pathways for end-of-life recovery. The results were remarkable. Hazardous waste dropped by 52%, and energy usage decreased by 30%. This is what happens when green chemistry principles move from theory into engineering practice. Green chemistry is no longer just about environmental responsibility. It's about smarter design, lower operating costs, safer manufacturing, and long-term scalability. Companies adopting these principles are seeing lower energy requirements, reduced waste and disposal costs, improved worker safety, and materials that meet growing market demand for sustainability. As industries push for cleaner, safer materials, whether in medical devices, automotive components, or packaging, green chemistry becomes a competitive advantage. Thank you for joining this session. I hope these insights help inspire your next sustainable polymer project.